Today's lecture is on the topic adaptive neural control for affine systems, multi input, multi output. Last class we talked about single input single output system. So, we will see that how the techniques that we learnt in the last class can be extended to multi input multi output system. This is the lecture on the module 3, which is neural control on this in this course on intelligent control. So, topics that will be covered today is a revisit of adaptive neural control for single input single output system. I just want to refresh your memory of what we discussed in the last class. The general form of multi input multi output systems, then directive adaptive control of MIMO system of the form. So, we are only considering a specific form of the multi input multi output system, where this can be written in the form Z1 dot is Z2, where Z1 is a vector and Z2 dot is equal to Fz plus Gzu, where Z1 and Z2 are vector, and of course, Z is Z1 transpose Z2 transpose. Okay. So, if Z1 is n1 dimensional vector and Z2 is n2 dimensional vector, then Z is n1 plus n2 dimensional vector. Okay. So, we will talk about when Fz is unknown, Gz is known, and when Gz is unknown, we do not know the solution. Simulation results for two link manipulator system will present as a whatever this solution we will get for this kind of nonlinear system, where we assume Fz to be unknown, and we will solve the control problem. Finally, the summary. So, single input single output affine systems, we will be revisiting that subject again today. A large class of single input single output nonlinear systems can be represented by the following affine systems. An affine system can be written as x1 dot is x2, x2 dot is x3, and so on until xn dot is fx, where x is the complete vector consisting of the elements x1, x2, x3 until xn, and where is written here x is x1, x2, xn, and plus gxu, u is a singular input, u and y are single input system. So, belongs to real line, and the control problem is find u so that xt follows a desired trajectory x desired. So, feedback linearization technique we discussed last class, that in general if I have this particular nonlinearity here, which is we call affine, then if we select this control law u to be of the form 1 upon gx minus fx kvr lambda 1 e n minus 1 and so on, until this is n minus 1th derivative of the error, and this is the first derivative of the error, plus x n desired xn dot, okay, where e is yd minus y is the output tracking error, and r is the we say filtered tracking error, which is n minus 1th derivative of error plus n minus 2th derivative of error, and so forth. So, power denotes respective derivatives. So, putting this expression of u in the system dynamics. So, system dynamic is simply your x n dot is f x g x u. So, if I replace this u here, okay, so I get x n dot in this side, and this side is in u you have this x n d dot. When you multiply this u with g x, you get x n d dot. So, bring to the side, then and then that by definition this term is minus. If you look at E is this one, then this particular term by definition becomes minus nth derivative of the error and equal to this side. If you look at this, minus f x will cancel with this f x. So, hence this is k v r plus lambda 1 E n minus 1 until lambda n minus 1 E first derivative. So, the closed loop aerodynamics becomes finally, if I look at here, if I take this one to this side, then this term will become r by definition here. This is my r. So, this will become, if I take to this side, this will become r dot. So, r dot becomes minus k v r, which is linear as well as stable, given k v and lambdas are positive parameters. Okay. So, these parameters are all positive, and they are such designed that this is a okay. So, this is feedback linearization. So, what did you see is that if my system is described by this form x n dot is f x plus g x u, and if I select control input is like this, then I am able to show that such a controller will stabilize the system. Also tracking will be achieved and the closed error feedback aerodynamics becomes r dot equal to minus k v r. So, now we extended this feedback linearization principle for adaptive control technique. Why we are doing adaptive control? Because we assume that in the dynamic which is given x n dot is f x plus g x u. If these f x and g x are known, then there is no need for adaptive control. But most of the situation, or in many situations, we do not know what is f x and g x. So, how do we solve this problem? Using the same principle, the feedback linearization concept. So, what we are trying to do here is that last class we discussed two cases where one is f x is unknown and g x is known, and the other is that both are unknown. So, we are considering the first case now, f x is unknown, g x is known. Then if we select the control law, which is 1 upon g x, you can see that this form is exactly as that of a feedback linearization control law, but with the exception that instead of f x, which is unknown, we have written f hat x, which is an estimate of f x. But we are saying direct adaptive control because we will not be estimating f x using the system identification principle, but we will be identifying f x hat using the principle of tracking error convergence directly. Hence, this control technique is known as direct adaptive control. So, what I am saying here that where the nonlinear function f x is approximated as f hat x using a radial basis function network, f hat x is w transpose phi x, w hat is the weight vector of the network. The update law for w hat is w hat dot is minus phi f phi into r. So, f is a positive definite matrix, phi is the radial basis functions using which the unknown function f hat x is estimated, and r is the filtered tracking error which we have already defined, r is e to the power which is there here, e to the power n minus 1 plus lambda 1. Okay. So, this is our filter tracking error. And using this filter tracking error, we have an weight update rule for estimating f hat x. So, in this method the idea is not to exactly identify what is f hat x, but to estimate f hat x in such a way the tracking error is converged. Okay. So, we proved this theorem. We are not going to prove this theorem in this class because we have already done it. I am just refreshing your memory. Similarly, we also proposed a control law for when this affine system both f x and g x are unknown. Okay. Again, for your memory here, I rewrite it f x plus g x u. So, in this the control law is given by u 1 plus u 2, where u 1 is similar structure except that here we have, instead of g x we have g hat x, and here instead of f hat x sorry f x we have f hat x, the estimate of f x, because we do not know f x and g x. And u 2 is a sliding mode term, which is the absolute value of g hat upon g l, absolute value of u 1 signum r, the sign of the filter tracking error. G L, the G L is lower bound of G x. So, what we are also assuming here, G x is either positive or negative. So, G x is approximated as G hat x using a radial basis function network. G hat x is P transpose psi x. P hat is the weight vector of the network. The update law P hat dot is minus G psi u r, and G is a positive definite matrix. Okay. And similarly, the weight update law for f x, which is f x hat is W transpose phi x. So, this is f x, and the W hat dot is also the same what we derived f phi r, right. So, this is we have two update law, sorry, weight update law. One update law for the weights of the neural network that approximates f x, and there is another update law here, which is the weight update law for the neural network that estimate g x. So, if these are the two update laws, then the control law given by u equal to u 1 plus u 2 will stabilize this nonlinear system. Now, adaptive control of MIMO system. So, using this two theorems we proved, the two theorems that we discussed now we have already proved in the last class. Today we will extend these concepts to the MIMO system. Let us see what is a MIMO system. We will now extend the application of proposed direct adaptive neural control to multi-input multi-output system. A general multi-input multi-output system can be written as x dot is f x plus g x u and y is c x. So, unlike the earlier case, what we are writing here is that here x dot is a vector, and as a whole this is the relation f is f x plus g x u, where x belongs to the n dimensional vector, f x also is an n dimensional vector, u is m dimensional vector, g is m into n dimensional vector, and y is p dimensional vector, and c is p into n dimensional vector in m dimensional matrix. So, in fact, this is a matrix, G x is a matrix and this is also a matrix. So, we are talking about a multi-output system. So, now this is a very general form, and out of this form we will consider a very specific form, which is this one, this structure, where this MIMO system is written like this. We can write many of the system dynamics, particularly multi-link robot manipulators, all categories of multiple robot manipulator, that is 2 link or more than 2 link robot manipulator. The dynamics can be written as x1 dot is x2, x2 dot is f1x plus g1 1 u1 until g1m um, x3 dot is x4, x4 dot is f2x g21x until g2mx um, and similarly finally x2n minus 1 dot is x2n and x2n dot is fx fnx plus gn1x u1 until gnm x um. Okay. So, so what you are seeing is that here that we have written this is a generic form of a specific multi-input multi-output system, where outputs are x1, x3, the odd numbered state vectors x1, x3 until x2n minus 1. For such cases, the system equation can be rewritten as z1 dot is z2 and z2 dot is fz plus gzu. So, what we are doing is that we are clubbing these equations, okay, and these equations we are representing by z1 dot is z2, and then obviously we are saying z1 is x1 odd number things x2n minus 1 transpose, and z2 is x2, x4, x2n. Okay. So, you see that if given 2 n state vectors, n state vectors can be represented as z1 dot is z2, and the next one z2 dot can be written as fz plus gzu, which you can see here, this one and this one. So, this representation is z2 dot is fx plus gx u. Okay. So, this is again the n dimensional vector z2, and fx x is 2 n dimensional, and gx also is n into m dimensional, because u is m dimensional. So, here this is our the class of multi-input system, multi-input multi-output system that we will be discussing today, where z1 is x1, x3 the odd number of state vectors, and z2 is the even numbered state vectors state elements. So, fz is f1 until fn transpose, and gz you can easily see gz is g11. So, this is g11 until g1m, g21 until g2m, gn11 until gnm. So, this is the elements, you just gather them, that forms gz, and then your final state vector z is actually 2 n dimensional, where each one here is n dimensional. So, direct adaptive neural control. The output error can be defined as E is yd minus y, and as you know that y is again n dimensional vector, because we are assuming that this is Z1 desired minus Z1, and since Z1 is the n dimensional vector, so this is valid. So, YD is Z1D is the desired output vector. Let us define a variable R, which is again on the form of a filtered tracking error. R is E dot plus lambda E, where lambda is a diagonal matrix with positive diagonal elements. Theorem 1, suppose that the nonlinear function fz is unknown while the function gz is known. Suppose also that fz can be approximated as f hat z upon equal to w hat transpose phi z using a radial basis function network, then the control law given by this expression u is g transpose into g transpose inverse whole multiplication minus f hat z plus kvr plus this term into E dot plus Z2 D dot. So, Z2 dot, this is actually dot. So, the desired one will stabilize the system in the sense of Lyapunov, provided W hat is updated using the update rho, okay, minus Fi R transpose. So, you see that here in the single input single output case R was a scalar, and in this case this is a vector, n dimensional vector. So, you see that when we did with using single input single output system, we had a radial basis function network that was estimating what is f x. So, if you see the weight vector here, which is w, this is a vector, and how many dimension? That dimension is L into 1 dimensional vector w. So, in case of single input single output system, the function f x is a scalar function. The RBF network has a single output as shown in the figure. The network weights constitute a vector w hat in this case, while when we do it multi input multi output system, so we have n outputs here. So, in this case this is no more a vector, w hat is a matrix. So, what is the meaning of this w hat here? In case of MIMO system, the function f x is a vector valued function. The RBF network has multiple outputs as shown in the figure. The network weights constitute a matrix w hat in this case. Now, we will go to the proof with this basic idea we have already actually described. We described that this control law with the weight update algorithm for f hat z, which is w hat dot is minus f I R transpose. If I have this weight update law for estimating f hat z, then this controller will give me the results that the actual output will follow the desired output. Okay. So, in this control law, Kv is a positive definite diagonal matrix, W hat is the weight matrix of appropriate dimension. Now, let us assume that there exists an ideal weight matrix W such that the original vector f z can be represented as W transpose phi z. So, and we can say here f dash z is W hat transpose phi z, where this W hat has to be updated. Okay. So, we have already given this rule of W hat dot is minus f I R transpose. So, can we say that given this as the weight update law, the this controller will stabilize the given affine system. So, now what I do is that my dynamic is, because f z is this one. So, z to z is f z. So, this f z is now W transpose phi z plus G z u, and this u is replaced by this equation here. So, the closed loop aerodynamics is obtained by putting u in this equation. So, the putting the controller u in the system equation, and after simplification we get Z2 dot is W transpose phi minus W hat transpose phi plus KVR plus lambda 1 E dot plus Z2 dot. Actually, if Fx would have been known, then these two terms would have cancelled, then we would have remained only with this term, which is a stable closed loop aerodynamic. But since these two are not exact, they are different. So, how do we stabilize it? So, we have proposed a control law for weight update. So, defining the error in weight vector is, earlier I told here that in this case W is a matrix. So, this is very important, and here W is actually a matrix. So, defining the weight matrix W tilde is according to this, we can write Z2 dot, this particular term is W tilde transpose. So, this is written as W tilde transpose phi plus these three terms KVR plus this term into E dot plus Z2 dot Z dot to desired. We have already defined R dot, this is not again. So, R dot we know, which is we have defined R to be E dot plus. So, if I recompute R dot is E double dot plus 1 into E dot. So, the symbol, this is simply a constant into 1 suffix 1 E dot, which is Z2 dot minus Z2 dot plus 1 E dot. So, this particular expression we derive from R dot, simply differentiating and then replacing in this case what is E double dot. So, E double dot is simply Z2 d dot minus Z2 dot, because so this combining this expression we get the closed error dynamics. The closed error dynamics is R dot is minus KVR minus W tilde transpose phi, which is the final closed loop aerodynamics. When we now analyze the stability of this using Lyapunov function. So, what we get is that this is our closed loop aerodynamics, okay, by replacing u in our system dynamic, which is f z2 f z plus g z u is z2 dot. So, this is our dynamics. If you replace this in this dynamic here z2 dot, if I replace this z2 dot here, then I get this expression. Now, so this is our closed loop dynamics, this is the closed loop dynamics. R dot is minus KVR W tilde transpose phi. So, then now consider a Lyapunov function candidate V is half R transpose R plus trace half W tilde transpose F inverse W tilde. F is the positive definite matrix. So, the Lyapunov function should be a scalar function, but W hat is a matrix in this case. We have taken trace because earlier we simply wrote this is W tilde transpose F inverse W tilde, but now we have taken trace because of the matrix, because this Lyapunov function has to be scalar. So, trace of a matrix, those of you do not know, if I take a 3-dimensional matrix, the diagonal elements is given by A11, A22, A33. So, trace of a matrix is A11 plus A22 plus A33. Okay. So, differentiating V dot, which is R transpose R dot, plus trace of W tilde transpose F inverse W tilde dot. Substituting R dot into above equation, so this R dot which we the closed loop dynamics, this is my R dot. So, if I give this equation, or if I replace this equation in V dot, which is R transpose R dot, so we may get a nice solution for this, which we have derived now. You can see that R transpose R dot plus trace of this thing with the W tilde dot. Substituting R dot into the above equation, in this equation, you get the rate of Lyapunov function to be R minus KVR minus W tilde transpose phi plus the trace of this particular term. Since W is a constant matrix, we can always write W tilde dot to be minus W hat dot. So, V dot, which we have already computed to be minus R transpose KVR minus R transpose W tilde transpose phi plus trace minus W tilde transpose F inverse W hat dot. By taking this example, using the properties of trace, we will utilize this theorem which says R transpose W tilde transpose phi is trace of W tilde transpose phi R transpose. So, we can further simplify this V at rate derivative of the Lyapunov function to minus R transpose KVR trace, okay. And we have so what we have done here is that this is our trace, this particular thing has been replaced by this here trace W tilde transpose phi R transpose. So, this is trace and this is also another trace. So, you can write traces minus W transpose phi R transpose minus W tilde transpose F inverse W tilde W hat dot, equating the second term of the above equation to 0. This one we want to eliminate. I can take out W tilde transpose to the right hand to the left side as a common, then I get simply phi R transpose, you see that phi R transpose plus F inverse W hat dot is 0, or this is my weight update law, W hat dot is minus F phi R transpose. So, if this is my update law, then direct control system direct adaptive control for nonlinear system is solved. So, further the proof of the theorem again. So, using the update law W hat dot, which we just derived, minus F phi R transpose. Now, let us see that whether the algorithm is convergent. So, V rate derivative of Lyapunov function becomes, according to our definition, which was so this V dot becomes, V dot is minus R transpose KVR, since V is greater than 0 and V dot is less than equal to 0. This shows stability in the sense of Lyapunov, so that R and W tilde are bounded, hence the proof. Furthermore, you can easily check this one. Again V double dot, if I have found V dot, then V double dot is minus 2 R transpose k V R dot is 2 R k V square, because R dot is minus k V R. So, this was negative, this becomes positive, plus 2 R transpose k V W tilde transpose phi, because this R dot is replaced by. So, the since R and W tilde are bounded, so as V double dot, the double differential of the Lyapunov function. Therefore, V dot is uniformly continuous. Thus, according to Barbalat's lemma, V dot tends to 0 as t tends to infinity. Hence, R vanishes with time. So, what we showed here by saying that this is my update law, I found out this is my rate derivative of Lyapunov function, which is positive negative definite, which is always negative for the values r not equal to 0. When r is equal to 0, this is 0. So, and further we are showing that V dot is uniformly continuous considering this term. Thus, according to Barbalat's lemma, if this is continuous, then this term will vanish, it will go to 0, this term will go to 0 as t tends to 0. Okay. So, r would vanish with time. And what is r? If you look at here, r we have defined r is this particular term, which is the filter tracking error. So, finally, error will converge to 0. So, now we will apply this particular application to this adaptive control theory to an actual system in simulation, and we take 2 link manipulator. The dynamics of a 2 link manipulator has been taken as an example of multi input multi output systems. For a 2 link robotic manipulator, the second and third link of a Puma 560 robot that we have taken, the dynamical equation which relate the joint torques tau 1 and tau 2 to the joint angles theta 1 theta 2 of the links are given as, where tau 1 is a 1 plus a 2 cos theta 2 theta 1 double dot plus a 3 plus a 2 by 2 cos theta 2. So, this is the coefficient of theta 2 double dot plus a 4 cos theta 1 minus a 2 sin theta 2, this the whole term multiplication with this term. So, the joint torque 1 is related with the joint velocities, acceleration, velocity, which is the Coriolis force theta 1 dot theta 2 dot plus theta 2 dot whole square by 2, and the gravity term a phi cos theta 1 plus theta 2. Similarly, the joint torque in second joint, which is a 3, this is the acceleration term, this is the Coriolis term, and this is your gravity term, where a 1 is 3.82, a 2 is 2.12, a 3 is 0.71, a 4 is 81.82, a 5 is 24.06. The 2 link manipulator system can be rewritten as, okay. So, this particular system, what I can do is that I can write theta 1 double dot is something and theta 2 double dot is something, but you see that each equation is written in terms of theta 1 double dot and theta 2 double dot. So, I have to eliminate, and then I have to find out the expression for theta 1 double dot. Similarly, I have to find the expression of theta 2 double dot, right, using other terms. So, doing that, what you are getting, theta 1 double dot theta 2 double dot equal to 1 upon d m22 minus m12 minus m21 m11 tau 1 minus v1 tau 2 minus v2, where m11 is given by this expression, m12 is given by this expression, m21 is m12 and m22 is a3. where V1 is given by this expression, this big expression, which is A4 cos theta 1 minus A2 sin theta 2 theta 1 dot theta 2 dot plus theta 2 dot whole square by 2 plus A5 cos theta 1 plus theta 2. Similarly, you can see that V2 has similar another expression A2 sin theta 2 theta 1 dot whole square upon 2 A5 cos theta 1 plus theta 2, and D is M11 M22 minus M12 M21. So, this is M11 M22 minus M12 M21. So, M11 M22. So, diagonal element multiplication minus the other diagonal element. Considering the state variable as x1 is theta 1, x2 is theta 1 dot, and x2 is theta 2, x4 is theta 2 dot, one can write x1 dot is x2 and x2 dot is 1 upon d, and then this quantity m22 t1 tau 1 minus v1 minus m12 tau 2 minus v2, and similarly x3 dot is x4. Similarly, x dot 4 is in this particular format 1 upon d minus m21 tau 1 minus v1 plus m11 tau 2 minus v2. So, you see that we said in the beginning of the class that some of the systems can be represented in this particular form. Okay. So, you see that this v1 is a function of the state vector x, and similarly v2 also is a function of state vector x. This is also a function of state vector. So, v2 is state. So, you see that v2 is a function of theta 1, theta 2, theta 1 dot, and so forth, and v1 is theta 1 dot, theta 2 dot, and theta 2. So, this is all the states are there here, one state is missing, but anyway in general they can be a function of this entire state vector. So, this can be represented if we define Z1 to be x1 x3 and Z2 is x2 and x4, then the system can be written in our general notation that we talked, which is Z1 dot is Z2 and Z2 dot is Fz plus Gz tau. And going back and reformulating the problem, we get Fz is F1 F2, which is 1 upon d, and this is my first term minus M22 V1 plus M12 V2, and the second term is M21 V1 minus M11 V2, and Gz is a 2 by 2 matrix G11 G12 G21 G22, and this is 1 upon d M22 minus M12 minus M21 and M11. So, this is the output y is Z1, and Z1 is our single link position, first link position and second link position. The reference output trajectories are taken as which is a Z1d is x1d and x3d is pi. So, this is a position angular position of the joint 1 and angular position of the joint 2. So, pi by 6 sin 2t, pi by 6 cos 2t. The control input, which is u g transpose z g g transpose inverse minus w hat transpose phi z plus k v this term, and this is the desired trajectory z2 d dot. So, where r is our tracking error E double dot plus lambda 1 E dot, and E dot is Z1 d dot minus Z1 dot. Okay. So, this is our control law. We have already said that this control law with the weight update law for W hat will stabilize the weight update law is we have already said F phi R transpose. So, this weight update law would surely stabilize the system. So, we have selected Kv is 30 0 0 30 means it is a 2 by 2 matrix, and lambda is 20 20 0 0. So, W hat is updated using the following update law. W hat, that is minus F phi R transpose, where F is taken as 20 0 0 20. The number of neurons for the radial basis function network is taken as 30. The centers of radial basis function network are chosen randomly between 0 to 1. Weights are initialized to very small values. Okay. So, if we do that, the simulation results would show the trajectory tracking for theta 1. You see that desired and actual absolutely no difference, tracking is so perfect. So, you see that we have achieved this tracking, and the RMS tracking error is found to be 0.0004, assuming Fx to be unknown. Okay. And of course, in the initial period we are not showing, we are showing the period when the trajectory has settled, means the transients are gone. In the steady state, the tracking is perfect because a very small value 0.0004. Okay. So, desired and actual, this is very perfect tracking. Similarly, here this is the trajectory tracking for theta 2, and again you see that this is the link angle theta 2, and according to time, and then the steady state from time 3 to 8 again. If we compute the RMS tracking error, this is 0.0006, and very efficient tracking, and correspondingly the control torque tau 1 and tau 2 that were found out to be like this, and you can see again in steady state the control torque is very smooth without any kind of fluctuation. So, very continuous torque. So, this implies that the proposed algorithm is very efficient, extremely efficient. Now, the what we did is that you see that if we go back to the control law, I do not know whether you noticed or not, this in control law we have this GG transpose my inverse, and you know that this is a matrix. In this case, the G is 2-dimensional matrix. So, GG transpose is again 2-dimensional matrix, but in general if I have a n link matrix, it is 2 links, so it is 2-dimensional. If I have a 6 link matrix, this is 6 by 6 inversion matrix. So, inversion means computation obviously is more. So, this point we can so G transpose inverse can be effectively computed using a recursive relation. So, we have one can work out for this, that how we can, instead of doing this inversion, we can find a recursive solution for it, so that this inversion can be easily computed. This is the first thing, comments. And the second thing is that when we consider Fx is known and Gx is unknown, sorry, Fx is unknown and Gx is known. Now, if I say Gx is also unknown, Fx both are unknown, this problem is still not solved in the literature, in control literature. So, when the nonlinear function G is unknown, the adaptive control problem becomes difficult to solve. This is an open research problem. In summary, in this lecture the following topics have been covered: adaptive neural control for single input single output systems is revisited, mathematical model is provided for a general class of multi input multi output systems, where we could represent even practical systems like multi-link robotic manipulators. They can also be represented in this particular format. Z1 dot is Z2, Z2 dot is Fz plus ZU. When Fz is unknown, then the solution to this control problem is already provided, and but of course we found that in this the control law includes an inversion which has to be replaced, which must be replaced by a recursive solution. Simulation results are provided for a two-link manipulator system, where we saw the tracking order is in the tracking error is in the range of 10 to the power minus 4. So, implying the tracking is very perfect. Direct adaptive control of multi-input multi-output system when both f z and g z are unknown is kept for the future work. This problem is not still solved. So, those who are further interested to work on this problem, I would like that you can follow these references, the Lewis, Jagannathan, S. L. Dirac, Neural Network Control of Robot Manipulators and Nonlinear Systems. This is a book published by Taylor and Francis in 1999. Spooner and Pacino, they have a paper on IEEE transaction fuzzy system, stable adaptive control using fuzzy systems and neural network. And Hay, Rife and Unbehaven, they have published a paper on IEEE transaction neural network or neural approach for control of nonlinear system with feedback linearization. And Choi and Farrell, nonlinear adaptive control using networks of piecewise linear approximators, IEEE transaction neural network volume 11 number 2. And this is our paper, Indrani Kerr and myself, neural network based direct adaptive control for a class of affine nonlinear systems. This is an International Symposium on Intelligent Control, Munich, Germany. Thank you very much.